I'm back again. Hi, my name is Lonnie, and today I'm going to discuss a few concepts in chemistry. One of the first concepts is we're going to talk a little bit about Avogadro's principle and how it relates to moles versus volume. We'll also talk about the combined gas law. Then we'll proceed to the ideal gas law, and ultimately we will do some derivations of the ideal gas law and incorporate molar mass as well as density. So having said that, let's go ahead and begin with Avogadro's principle. Let me go ahead and write that, Avogadro's principle. Now remember, Avogadro's principle states that for any gases that in fact are at the same temperature and the same pressure will in fact have the same number of parts. So remember and recall that Avogadro's constant in terms of particles per mole was 6.022 times 10 power 23. And so essentially any gas, again, any gas or gases at the same pressure and temperature will in fact have X number of particles per mole. Now one of the other things that Avogadro did, let me scroll that up, one of the other things that through some experiments, Avogadro identified a relationship between mole versus volume. And in an experiment, he identified that at some given conditions, and those particular conditions were temperature was at 0 degrees Celsius and pressure was equal to 1.00 atmospheric pressure or ATM, that at these given conditions that the volume of 1 mole of gas would in fact equal 22.4 liters. Let me scroll that up. Now what does that mean? That means that, for example, if we do have a gas at these particular conditions, now note that these conditions are known as standard, I'm going to abbreviate, standard temperature and pressure, or commonly abbreviated as STP. So again, from this we can identify two different conversions. If we are in fact converting, let's say we're given mole or moles, we can convert moles to liters. Of course this is in volume. Or we can convert liters to mole. And the particular conversions for mole to liters, in fact, would be 22.4 liters per 1 mole. Hence, this would be moles to liters, and we would ultimately get the number of liters. Or we can convert, let's scroll that down, liters to moles, and hence we would use the 1 mole to 22.4 liters, and hence we would therefore get mole. So this becomes very significant when we're doing some calculations with respect to gases, again with respect to the ideal gas law, and even when we're doing some gas stoichiometry, which we will at a later time talk about gas stoichiometry. Okay, so having said that, let's continue on. Now note, we want to go ahead and do a problem calculating what the molar volume is. And let me go ahead and we'll read a problem here. Let's go to problem number 1. Problem number 1 states, calculate the volume that 2.00 kilograms of methane will occupy at STP. Now recall, one of the first steps that we do in any of these kinds of problems is identify the unknown versus the data that is given or the known data. So my unknown is we are calculating volume. This is what we're looking for, volume, let's see, of methane. Now note, after we identify the unknown, let's calculate and identify what our given data is. First of all, we were given a mass, and that mass is 2.00 kilograms of methane. Okay. We're also given temperature, standard temperature, which is 0 degrees Celsius or 273 Kelvin. Now note, in these problems, temperature must be in Kelvin, not in Celsius. So if you're given Celsius, convert Celsius to Kelvin by adding 273. We're also given the standard pressure, which in fact is 1.00 atm. Okay, and that is about all the information that we need. So let me scroll that up again so we have a little room to work with this. Again, we're looking for volume. So note, we're given 2.00 kilograms of methane, CH4. Let's go ahead and calculate the molar mass for methane. CH4, in fact, the molar mass of that would equal 12 plus 4, so we have 12 plus 4, which in fact equals 16 grams per mole. Okay, this is for methane. Now we're originally given 2.00 kilograms, okay, and we want to, in fact, convert that to grams, and then we want to convert the grams to moles. This is what we can do. Take the 2.00 kilograms, divide it by the 16 grams per mole, okay. Now let's use a conversion unit to get rid of our kilograms and convert the kilograms to grams. And so hence we have 1 kilogram equals 1,000 grams. Okay, now we've got the conversion unit here. So in fact we have kilograms that are being canceled out here, and we also have grams that are being canceled out. And now let's do a conversion factor in terms of, we're looking for volume, so we are going to get a conversion factor of per every 1 mole at standard temperature, it is 22.4 liters. Hence our mole will in fact cancel out, we're left with liters, and hence our volume for this particular problem of methane V would therefore equal, after we do a calculation on this, we should get a volume of 2.80 times 10 power 3 liters of methane, and we've solved that. Now, recall that we solved this, there were several things that we knew. We knew that, of course, that the conditions were at standard temperature and pressure. Knowing that they were at standard temperature and pressure, we could then use the conversion factor, 1 mole or 22.4 liters, or 22.4 liters per 1 mole. And we can therefore calculate without having to use the ideal gas law. Hence our value, 2.80 times 10 to the 3 liters of methane. Okay, let's go ahead and move forward. Let's continue on. Now, let's talk a little bit about, let's talk a little bit about the combined gas law. Okay, combined gas law. Many of you have already studied this, and let me just give you a few facts. Conventionally, how it's expressed as P1V1 to T1 equals P2V2 to T2. Now note, on this side, right here, right side versus left side, these would be initial, I'm just going to put IC, initial conditions, whereas these, on this right side, would be new conditions. New conditions, okay? Let me go ahead and scroll that up. Now, let's rewrite that. Note that for a sample of gas, the relationship between pressure, volume, and temperature will always be the same, i.e., we can rewrite that, the combined gas law, we can rewrite it as PV divided by T equals a constant. And I'm just going to call that constant K. Let me put it in parentheses, constant. Okay? Well, let's look at this combined gas law. And let's look at a couple conditions. The first condition is, let's say, for example, pressure and temperature are constant. That's one item. Let's say that we increase the amount of gas that is present. So we increase the amount of gas. And I'm going to say we increase N, or mole, amounts of gas. What effect will that, in fact, have on my volume? Hence, the volume will, in fact, with an increase in the amount of gas, the volume will, in fact, increase also. So what does it tell us about the relationship? As we increase the amount of gas, also volume increase, so that tells us that volume has a direct relationship with respect to N, or amount of gas. Well, let's look at one more condition. Let's say, for example, again, let me rewrite this. PV T equals that constant. Let me scroll that up so we can see that. Let's say, for example, the conditions are where volume and temperature are constant. And again, that's one circumstance. And again, we increase the amount of gas. We increase the amount of gas. And again, I'm representing that increase by N or mole, if you will. What is going to happen to pressure? Pressure will, in fact, as we increase the amount of gas, pressure will, in fact, also increase. So what does it tell us? Well, it tells me this, is that as the amount of gas, or N, increases, there's a direct relationship with pressure. Pressure so likewise will increase. Well, what can we do with that information? Let's rearrange. Let me scroll that up again. Let's rewrite our original combined gas law equation, PVT equaling K. Now we note that P and V are directly related to N, or the amount of gas. So with that, we can incorporate N, or mole, into our combined gas law, and hence let's rewrite this as PV divided by N, amount of gas here, or mole, equaling a constant. And we have now identified a new relationship that incorporates not only pressure, volume, temperature, but also mole, or the amount of gas. Equaling a constant for any given amount of gas, we note that this particular constant is known as the ideal gas constant. Ideal gas constant. We also note that this particular ideal gas constant is symbolized or expressed as uppercase R. And so hence, we can rewrite this particular equation of PV NT equaling a constant. We can rewrite it as PV NT equaling R. And let's rearrange it in the conventional way and describing the new law that we have, which in fact is called the ideal gas law. Again, we've incorporated N into this. And that ideal gas law is expressed conventionally as PV equals nRT. Now note that R equals the ideal gas constant. And that particular constant has, depending on how pressure is expressed, that particular R constant can also be expressed with different values. So for example, if pressure is expressed in ATM, the value for R would equal 0.0821. Okay? Well, let's identify another unit that's commonly used for pressure. Let's say, for example, pressure is expressed in kilopascals. Another common unit for pressure. R, therefore, equals a value of 8.314. Okay? Let's go one step further. Let's express pressure in terms of mmHgs, millimeters mercury, or torr. And hence the R value, or the ideal gas constant, would in fact equal a value of 62.4. Okay, so far so good. So let's reiterate what we've just gone through. We've got a new law which is known as the ideal gas law, expressed as PV equals nRT, where R is equal to our ideal gas constant. We've got several values of that based on pressure and how it's being expressed. And so hence, let's go ahead and let's work a problem regarding the ideal gas law. Okay, so let's go back. We're going to go back to problem number 2. Well, here it is. Again, this is a problem utilizing our new equation from combined gas law to ideal gas law. And here's the problem. Calculate the number of moles, we're looking for N, of ammonia that are contained in a 3.0 liter vessel at 300 Kelvin with a pressure of 1.50 atm. Okay, well remember the first thing that we want to do is we want to, in fact, express, let me scroll that up. We want to express what we're looking for. So in this case, we are looking for N, which happens to be moles of the ammonia. Okay? This is our unknown. This is what I'm looking for. Let's identify the knowns that we have. We, in fact, have our volume equals 3.0 liters. We were also given a temperature, and we were given it in Kelvin, so therefore we don't have to convert it from Celsius to Kelvin. No, that's standard unit used in these types of problems. And then our pressure was given at 1.50 atmospheric pressure, or ATM. And note, when pressure in fact is expressed in ATM, what R value do we use? Well, we in fact use R equals 0.0821. Okay, we're ready to solve for n. So let's go ahead, next step, after we've identified the unknown, the data given, let's rewrite the equation, PV, in its standard equation. Let's rearrange this. This is what we're looking for. That's my unknown. Let's rewrite that such that n is in terms of pressure, volume, gas constant, temperature, so hence n equals PV divided by RT. Let's now plug in the data that was given to us. We were in fact given 1.50 ATM. Okay, times our volume. Volume was 3.00 liter. Okay. We were also, our gas constant based on the ATM is 0.0821. And our temperature was expressed at 300 K. We can do a calculation on this, and hence we will come to a value of the number of moles of NH3 in fact equals 0.18 mole of NH3, or ammonia. And we've utilized the ideal gas law to calculate. Well, let's go ahead and move forward, okay? Let's talk a little bit about the ideal gas law, and in fact, specific, let's move this just a little, make some room for us. Okay, let's talk a little bit about the ideal gas law. Let me rewrite it. PV equals nRT. Now let's identify this, and we want to derive a new equation by expressing moles in another quantitative value, which in fact is, mole, as you recall, is mass in grams divided by the molar mass. I'll put this in parentheses, molar mass. Big M for molar mass expressed as a big M. Now we can take this particular new expression for N, we can substitute it in N, rearrange the ideal gas law, and then we can rewrite this equation. So let's plug this in. We'll do it in a couple steps, not to get too far ahead of you. Okay, so we've got PV equals, again, we've got little m RT divided by big M. Okay, let's rearrange this and let's identify molar mass in terms of mass, pressure, volume, gas constant, and temperature. So we're gonna isolate big M. So we have big M, therefore equals mRT, little m for mass, divided by PV. And hence we have got a new derivation expressed in terms of molar mass equaling mass, gas constant, temperature divided by pressure, volume. Well, let's go ahead and move forward. Let's do a problem on that. Let's do a problem here with this new expression of the ideal gas law, or derivative, if you will. And we're going to go to problem number 3. Well, here's problem number 3. It reads as such. A 2-liter flask is filled with ethane C2H6 gas from a small cylinder. What is the mass? Note that we're looking for the mass of the ethane in the flask if the pressure is 1.08 ATM and the temperature is 150 centigrade. Okay? Well, let's see. First of all, let's write our unknown, and we are looking for, let's see, what is the mass? We're looking for little m, the mass of ethane. C2H6, okay, mass of ethane equals question mark. Let's identify the data that has been given us. Let me extend this, scroll that up a little, and then we'll write the data. This is what our unknown is. Here's the data that was given. Our volume was expressed at 2.00 liter. We were also given a pressure equaling an ATM, 1.08 ATM. We were also given a temperature. Of course, this was expressed in Celsius, and it was expressed at, let's see, 15, whoops, let's express it at 15 degrees Celsius, okay? We'll change that to 15 degrees Celsius. So that was expressed at 15 degrees Celsius. I'm going to convert it to Kelvin. We have to work in Kelvin in terms of temperature, so hence that would be 273, so that would be 288 Kelvin. Here's the temperature we'll be working with. And our R factor, in terms of the gas constant, We've got pressure expressed in ATM, so therefore R must be 0.0821. And let's get the molar mass of C2H6, and that in fact happens to be 30 grams per mole for the ethane. Okay, well, we are good to go at this point. Let's give the expression up. Let's rearrange this first of all. Well, we know that molar mass equals MRT, again, divided by PV. Let's rewrite that, divided by pressure volume, product of. We want to rearrange it such that mass is expressed in molar mass, pressure volume, gas constant. So hence we will write little m, therefore equals M, big M, PV divided by RT. And we're ready to plug in the given data that we have and solve for our mass of ethane. So let's go ahead and plug in the values. Values would be 30 grams per mole, which in fact would be my molar mass. The pressure was given to us at 1.08 ATM, and the volume was given at 2.00 liter. Okay, so far so good. On the bottom we've got gas constant, which was, in terms of pressure was ATM, so therefore our corresponding gas constant would be 0.0821, excuse me, times our Kelvin, which in fact was 288 Kelvin, originally given in Celsius at 50 degrees, and hence we can solve this. Let's plug this in, and hence we will get a mass of approximately, once we do a calculation here, where little m, again this is of the ethane, equals approximately 2.74 grams. And this is our answer, again, with utilization of our first derivation in terms of molar mass of the ideal gas law. Okay? All right, let's move ahead. Let's take this one step further. Okay, let's move this. Let's take this one step further. Now, no, this is what we were given in terms of molar mass, and this is the first derivation. M equals little m RT divided by VP. Now, I specifically wrote it in that format so we can show another substitution that we're going to do at this point in time. Now, note that we've got a relationship here in this particular derivation, and that particular derivation that can be associated with another function, which in fact is m divided by big V equals density. And density typically is expressed as uppercase D. So we in fact can take the mass divided by volume and substitute D in its place, and then rearrange it such that density is expressed in terms of MRT. Let's do that. So hence we substitute D for M divided by V, which in fact is grams per milliliters or liters. So hence we have big M, molar mass, equals DRT divided by P. Let's rearrange this such that D is expressed in terms of molar mass, pressure, RT, and hence we now have got, let's extend that up, we have got a second derivation that expresses the ideal gas law, however, in terms of density. So let's go ahead and do a problem on this. And here's the problem. Let's scroll back here. Go back to our problem screen. Okay, here's the problem that we're going to do. What is the density? So note that we're looking for density. We're going to use the new derivation that we came up with in terms of density. Note that what is the density of a sample of nitrogen 2, diatomic nitrogen gas that exerts a pressure of 5.30 ATM in a 3.50 liter container at 125 degrees Celsius, okay? Well, what's our first item that we do? First thing is, let's identify what we're looking for. Well, our unknown, in fact, happens to be density. So we, in fact, are looking for density. And the density, of course, is density of N2, diatomic nitrogen. Now, let's identify the data that they've given us. Well, they gave us, first of all, they gave us pressure, which was expressed in ATM at 5.30, again, in ATM. They also gave us a volume, and the container size was 3.50 liter. We were also given temperature, and that temperature was expressed in Celsius. Let's convert it to Kelvin. So when we convert it to Kelvin, we should in fact get 398 Kelvin. And we need our ideal gas constant. Because pressure is expressed in ATM, let's use that particular corresponding value for the ideal gas constant, which is 0.0821. Let me scroll that up a little more. Okay, we are ready to solve for density. So having said that, let's write our equation for density. We call equals molar mass times the pressure divided by gas constant times temperature. Let's go ahead and plug in the data that we've been given. Well, first of all, we need to find the molar mass. So let's restate that. Let's go up here. Recall that the molar mass of M2, in fact, equals 14 times 2, or 28 grams per mole. Now we have our molar mass. So now we have the data that we need. Let's go back down here. This is 28 grams per mole. That's for my molar mass. The pressure was times 5.30 ATM. So far, so good. Our gas constant in this case is 0.0821 as a result of ATM. And my temperature was converted to 398 Kelvin. And so hence we've got all the values that we need to calculate for density. And when in fact we do calculate that, we come up with a value of 4.54 grams per liter, and hence this is in fact my density for that. Now note that liters, of course density oftentimes is expressed also in milliliters, but our liters in fact comes from my constant there, which is liters ATM, mole, Kelvin, and note that every one of these, mole is canceled out, Kelvin is canceled out, and we are left with liters, grams, so hence, so you know, grams per liters, hence my grams per liters, or 4.50 grams per liters. And that is it, that's a wrap. We appreciate your time. And we'll be back with you again with some more chemistry. More specifically, we're going to talk about the next time about gas stoichiometry. Bang! Thank you. That's a wrap. Have a great night.